Hey there, we're going to look at how we factor trinomials this time with a new method, guess and check. So guess and check will break it into three scenarios: when a is equal to 1, when a is not equal to 1, and then a special case where we have a difference of perfect squares. So technically you can use the same guess and check method on all of those, and that would be the method that is used for when a is not equal to 1, and we'll talk about that a little bit. But if you can notice that a is equal to 1, it can be cut a little bit short in terms of the length of the process. So factor by guess and check when a is equal to 1. So guess and check is an alternative to factor by grouping with the same types of problems. You don't need to split it into 4 terms when you're factoring by guess and check. So essentially the purpose or the concept behind guess and check is that it is reverse distribution. So when we have something like a plus b times c plus d, remember we distribute by doing the first term multiplied by the first term, and then we do the first and the last. We do the inner, and then we end up doing the b times d, which I'm going to put in purple here, right here, the last term of each one. So that's that FOIL, first, outer, inner, last. So we are going to use that reverse FOIL, essentially reverse distribution, when we're doing guess and check. So I'm going to talk you through it in general with a slightly more detailed process, and then you'll start to see a pattern when a is 1 of how you can essentially skip a step or jump to a conclusion a little easier. So when we have trinomials and we are factoring, we're going to go ahead and set up our 2 sets of parentheses that will be binomials in the end. So x squared minus 7x plus 12. Instead of trying to break that negative 7x up, what we're going to do is we're going to break down distribution, the reverse distribution. So to get x squared, if I already had binomials, that would have come from the first 2 terms being multiplied together. So if you think about what can I break that x squared into, that's going to be x times x will get you back to x squared. So that's going to be in the first part of each parenthesis. Then I'm going to look at the end. I'm going to look at that constant. And I personally would ignore the plus sign for now, just look at the number itself, 12. So think about the factors of 12. We want 2 numbers that can go at the end of each parenthesis, and they can essentially be like the b and the d here, and multiply together to give you that 12. So factors of 12 are 1 and 12, 2 and 6, and 3 and 4. So going through this list, just like or similar to when we did grouping, we're looking for 2 numbers that when a is equal to 1, so when this is 1x squared, those 2 numbers just have to go to that middle term, that negative 7x. So in this case, that's going to be the 3 and the 4. Now, I want to talk about for a second why that essentially works. And if you think about these inner and outer sets of multiplication in the FOIL, those are always going to be your like terms when we are combining like terms after we've distributed. So we check our inner and our outer products, and the inner product and the outer product combine to be that middle term. So for example here, the guess and the check part is going to be picking a pair here that we can place at the end of each parenthesis. So for example, 3 and 4. And the inner product, wherever you put the 3, wherever you put the 4, the inner product is going to be these 2 multiplied together. So that would be 3x. The outer product would be x times 4, which is going to be 4x. And we need those to combine to that middle term, which is going to be negative 7x. To get negative 7x, this is where the signs come in. Negative 7x, we need to make sure that these have the proper signs to combine to be negative 7. So they would both need to be negative, which would mean this 3 would be negative and this 4 would be negative. And the last thing you want to triple check is that negative 3 times negative 4 gives you the sign that goes with the 12 that we have in our constant spot. So negative times negative is positive, so we are good to go there. So our final factored form would be x minus 3 times x minus 4. Now on number 2, we have x squared plus 3x minus 18. x squared plus 3x minus 18. We can really think of the same way. We can set up those two sets of parentheses, and our x squared is going to tell us what goes at the beginning of each parenthesis. So that's going to be x times x gets us back to x squared. And then we look at that 18 at the end of the parentheses. And I know it is negative. We'll come back to that in a minute. But looking at just the 18 in general, the factors of 18 are 1 and 18, 2 and 9, 3 and 6. 4 doesn't work. 5 doesn't work. We're back to 6, which is already on our list. So now we look at our factors here, and you can essentially guess and check. You'll start to see the pattern, like I mentioned earlier, that they have to add to be this middle term. So if you look at this list, because A is 1, when A is not 1, it will change a little bit. But because A is 1, we can just look at each of these pairs, and we can see which pair can either add or subtract in some way with positives and negatives to give you a 3x, positive 3x. So 1 and 18 isn't going to work, 2 and 9 isn't going to work, 3 and 6 should work. So let's put 3 and 6 there. Doesn't matter which one you put first, which one you put second. Now we're going to check the inner and the outer product. So remember, the inner product and the outer product combine together to give you that middle term 3x when we distribute. So inner product is 3x, outer product is 6x, and we need those to become positive 3x. To do that, we would need a negative 3. 6 minus 3 gives us positive 3. So then to get a negative 3 as the inner product, that would be a negative here. To get positive 6x, we need a positive there. And that one last step to check is going to be negative 3 times positive 6 gets us back to that negative 18, which is what we needed. And so x minus 3 times x plus 6 is going to be our factored version of number 2. So now let's look at the same thing, but when a is not equal to 1. So it's essentially the same process, but we can't just look at the factor list and know immediately which pair of factors is going to work because we have a number other than 1 in that first spot. So let's take a look at 2x squared plus 9x plus 10. We're going to start the same way, two sets of parentheses, and we are going to start with that first term of 2x squared to figure out what goes at the beginning of each to multiply back to 2x squared. Because remember, when we distribute two binomials, which is essentially what we're trying to get back to is two binomials, when we distribute those, we have the first, then we have the outer and the inner, and then we have the last being multiplied together. So we're going to start with the first, which is this first term here and first term here. So if I put an x in each spot like I did before, that would just get me to an x squared, but we have 2x squared. So we need to think of the factors of 2, whatever number's in front. Luckily for us, that's just 1 and 2. So one of these is going to be 2x and one of them will be a 1x. It does not matter which one is 2 and which one is 1. And again, because it's 1x, you technically don't need that 1 with the x. Next, we want to go ahead and look at our constant, just like we did on the last example. So 10 is our constant. So list the factors of 10. 1 and 10, 2 and 5, 3 doesn't work, 4 doesn't work, 5's already on our list. So this is our full factor list for 10. Now, we can't just say, oh, 1 and 10 work or 2 and 5 work because they add to this 9x. It won't work that way when we have a value other than 1 for our a. So because our a is 2 at the beginning in front of the x squared, it won't quite work. So instead, we want to go ahead and guess and check. So you're going to start with either 1 and 10 or 2 and 5. I'll start with 1 and 10. And we are going to check the inner product and the outer product. Just like on the previous ones, we need the inner and the outer product to combine to that 9x. So inner product here would be 1x. The outer product is not going to be 10x because we have this 2x here, unlike the previous problems when a was 1. 2 times 10 is 20, so that's going to be 20x. And we need those to combine somehow to be 9x. 1 and 20 are not ever going to add or subtract in any way to give you 9. So we know that those do not work in the format that they are written. So I'm going to switch the 10 and the 1 and see if it works that way. 10 times x is 10x. 2x times 1 is 2x. 10 and 2 cannot add or subtract in any way to give us 9. So what that tells me is 10 and 1 are not going to work. And so then we move on to 2 and 5. So if I put 2 here and 5 here, 2 times x is 2x. 2x times 5 is 10x. Again, those are not going to add or subtract to 9. So we do need to swap their locations and see if that will work. 5 and 2. So we have 5x as our inner product. We have 4x as our outer product. 4 and 5 can add to be 9 if they are both positive. So if I put a plus in front of the 5 to give me a positive 5x when I multiply, and then for the outer product to be 4x, we need a positive 2. And the last thing you want to triple check is that positive 5 times positive 2 gives us that positive 10. So because it does, then we are good. 2x plus 5 times x plus 2 is your final answer here. So let's look at one more example where a is not 1. So looking at this, we will go ahead and set up our two binomials. Look at your first term, 3x squared will break into 3x and x because 3x times x gets us back to 3x squared. Then we look at the 4 at the end. 4 is at the end, so we need the factors of 4, 1 and 4, 2 and 2. And then we need to check our inner product and our outer product so that they combine to be that middle term of negative 8x. That's our end goal. So I'm going to just go ahead and guess and check. So I'm going to go ahead and put a 1 and a 4 here. 1 times x is 1x. 3x times 4 is 12x. 1 and 12 are never going to add or subtract to give you negative 8. So I'm going to go ahead and switch the 1 and the 4 and see if it works swapped around. 4 times x is 4x. 3x times 1 is 3x. 4 and 3 will never add or subtract to give you negative 8. So 1 and 4 are off the table. So I can go ahead and move on to 2 and 2. We put 2 here, 2 here. Now, those are the same numbers, so swapping them won't work. So if it doesn't work, then that would tell us that this is not factorable, which is possible. So 2 times x is 2x. 3x times 2 is 6x. 2x and 6x can give us negative 8 if they are both negative. So that would mean this one would need to be a negative, so the inner product is negative, and this 2 needs to be negative, so the outer product is negative. And that last thing to triple check, negative 2 times negative 2 does get us back to the positive 4, which is what we need from that multiplication. So our answer here would be 3x minus 2 times x minus 2. Now, I do want to note, you don't have to go in the order of the factors. So I did to show you what happens when you do get a wrong factor and how you have to switch them and check them that way. But you'll start to get in a habit where you start to see the patterns, and you might be able to choose the factor correctly the first or second time and not really have to go through all of your options. So now we have a special type of factoring by guess and check. So if we have a difference of perfect squares, which we've talked about briefly, but a difference of perfect squares is just a perfect square minus another perfect square. Remember that perfect squares are numbers that have a whole number times itself that gives you that number, or a variable times itself that gives you that number. So for example, 1, 4, 9, 16, 25, 36, so on and so on, are perfect squares because 1 squared is 1, 2 squared is 2. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, so on and so on. So there's a whole number times itself that gives you 1, that gives you 4, that gives you 9, that gives you 16, so on and so on. So same thing works with with variables and their exponents. So for example, x squared is really x times x. So x squared is a perfect square. X to the 4th is really x squared times x squared. So that's a perfect square. So when we have a difference of perfect squares, that is just subtraction between any two perfect squares. So x squared minus 9 is a difference of perfect squares because x squared is a perfect square and 9 is a perfect square. 4x squared is minus 1 is a difference of perfect squares because 4 is a perfect square, x squared is a perfect square, and 1 is a perfect square. So not only do the variable and the constant have to be perfect squares, but if there's a coefficient in front of the x squared, it also has to be a perfect square for this pattern to work. So before I go through what that pattern is, I'm going to show you how you could factor this the same way with guess and check by turning it into 3 terms. So this, when we have a difference of perfect squares, it's going to be missing that middle term, which just means that really it's a 0x that's there. So if you wanted to, you could rewrite both of these as 4x squared plus 0x minus 1 and x squared plus 0x minus 9. And you could go through the process. I'll show you on the first one. You could go through the process of figuring out, okay, x times x gets us back to x squared. Look at the last number, the constant 9. Factors are 1 and 9, 3 and 3. And if I need to pick 2 numbers so that the inner product and the outer product combine to that 0x in the middle, just like we did on those previous ones, if I try 1 and 9, 1 and 9 will be the inner and outer products, 1x and 9x, and that won't give you 0. So you'd go through your process and you'd find that 3 works. To have 3x and 3x give you 0, one of them needs to be plus and one of them needs to be minus. It doesn't matter which one is plus and which one is minus, but it's going to be the same binomial, but one will be plus and one will be minus. And we saw that with those special types of distribution. And I mentioned then that it's important that you notice this, or it can be helpful and time saving to notice this. If you have a difference of perfect squares, you can jump straight to x plus 3 and x minus 3, or whatever your numbers are, by essentially just looking at what is the square root of each term. And that's going to be the first and the second term. And then there will be a plus sign in one binomial and a minus sign in the other. So a and b come from the square root of each of these terms. That's what gives you a, and that's what gives you b. And then again, you're going to have 1 plus and 1 minus when you write this out. So we could have jumped straight to x plus 3 and x minus 3 instead of going through that entire guess and check format. So over here, when I notice that this is a difference of perfect squares, I can jump straight to 4x squared. If you think about square rooting the 4, you get 2. Square rooting x squared, you get x. Or you can think about what times itself gets you back to 4x squared. 2 times itself is 4, and x times itself is x squared. So you can think about it that way as well. It's up to you. And then you want to look at that last term, 1. And 1 is just 1 times 1. So that's going to be 1 at the end. 1 plus 1 minus. And that's how we factor. So again, if you can notice those difference of perfect squares, then it can save you time in factoring to realize that it's just going to be the plus and the minus versions of the same binomial. Okay, so let's go ahead and take a look at multiple choice, an example of multiple choice, and asking you to factor an expression, a quadratic expression, but how we might actually be able to just use those answer choices to rule out or eliminate some answers and maybe not even have to factor ourselves. So if it's a multiple choice problem where it's asking you to factor, remember that this is just the opposite of distributing. So I could sit here and I could think about, okay, if I distribute this out, 5 times x is 5x squared. 5x times 4 is 20x. 3 times x is plus 3x. And 3 times 4 is plus 12. While the first term and the last term match, the middle term of 19x is not received or gotten to by doing 20 plus 3. That does not work. So I can cross out a. Now you might think, how in the world is this quicker than just factoring it? But you'll start to notice, especially depending on the answer choices, if you just multiply that first set together, x times 4x is 4x squared. When you go to multiply the rest, there's not going to be any more x squared terms to combine with that. So that does not match this 5x squared. So that means b I can cross out. I also see that d is the same way. 4x times x gives me 4x squared, which is not going to match 5x squared. So I can cross that one out. And because I already crossed out a, that tells me that c should be the correct answer. You can double check it by multiplying it out. And you'll see you get 5x squared plus 15x plus 4x plus 12. And that 15x plus 4x does combine to 19x. And so C would be your correct answer on that one. So some of this you may not even need to write out. You may be able to see, oh, these multiply to the correct thing, or these don't, or I can rule this out because of this, so on and so on. So sometimes it's helpful to look at eliminating those choices on these types of problems instead of going through the factoring process. So we talked a lot in this lesson about factoring by guess and check, when A is 1, when A is not 1, and if we can remember those difference of perfect squares, we can remember that shortcut and not have to use guess and check. So remember, really the key things with guess and check is really just that distribution piece, that the first two have to multiply to the first term. The last two have to multiply to that constant. And then we check the inner and the outer product need to combine to that middle term, that bx. Okay, so that's the key piece with guess and check. So again, guess and check can be used on any of those trinomials, but it can be helpful, especially on the difference of perfect squares. When you have difference of perfect squares, remember the a plus b and a minus b, 1 plus 1 minus. That pattern is extremely helpful in saving time if you can memorize that. Notice the difference of perfect squares and then use that pattern.